Hey, we got a lot to cover today too. Man, I'm gonna try to do this differently than I did yesterday. We're gonna try something a little different. So if you remember last week we learned about the fundamental theorem of algebra, right? That says if you have an equation, it's like 2x to the ninth minus 5x squared plus 6. It wants to know how many solutions there are to that. Fundamental theorem of algebra says there's 9. Because the largest exponent will tell you how many solutions there are. And since it was x to the ninth, that means there's 9 solutions. Now, it could be that some of those solutions are imaginary solutions. They may have a 3 plus 2i type solution. It could be that some of those solutions repeat. Maybe x equals 2 is a solution 3 times. X equals 2, x 2, x equals 2. Maybe, there could be repeating solutions, but there are 9 solutions of an x to the ninth equation. That's what the fundamental theorem of algebra told us. And then we had the factor theorem and the remainder theorem. And the factor theorem said if we divide a polynomial, if we've got 5x to the 4th minus 3x squared, all that, and we divide it by x minus 2, either by long division or synthetic division, however we want to divide it. If we divide it by x minus 2 and the remainder is 0, then x minus 2 is one of the factors of that big equation. So we can factor that out, and then we'll have the rest of it, and we keep factoring. That was the factor theorem. The remainder theorem said that if instead of dividing by 2, like on that x minus 2, if we instead of dividing by 2, if we substitute 2 into the equation, that will tell us what the remainder is. The remainder theorem. That'll tell us what the remainder is. If the remainder is 0, then we know that 2 is one of the solutions. So that's the theorems we learned last week. This week, we're going to learn about the rational root theorem, and Descartes' rule of signs. So a lot to go through, but I'm going to start it a little differently this week. I'm going to start this a little differently. So knowing what we know last week on finding solutions, finding factors, let's go ahead and just look at our usual stuff as far as what are we doing this week as far as in Buzz. So if I put up the grade screen right off, you see that, let's see, the 22nd is last Sunday with just the theorems of algebra. That was the only thing we had, and that's where we learned those 3 theorems. This week, we've got 2 lessons and a quiz. The rational root theorem and Descartes' rule of signs, and then solving polynomial equations, which is basically using all of these theorems. So it's not really anything that new in this second lesson. It's just putting all this together. And then the quiz, which kind of covers the first 5 lessons here. So there's a quiz, there's this, but this is new, rational root theorem and Descartes' rule of signs. So here's how I'm going to start this week. I was going to go through the lesson right off the bat, but instead, I'm going to put up this equation. This is a good time to have some pencil and paper. You'll want to take some notes over this week's stuff because it's very, very different. But let me put this equation on the same. And let me say, all right, what are the solutions? You're like, what? What are the solutions? Are you kidding me? Yeah, what's the solutions? If we factor that, if we found like x minus 2 is a factor, that means x equals 2 is a solution, right? So we need to factor this. So anyone got any ideas how we factor that? How can we find factors of that? How can we figure out what the solutions are? That's quite a thing there, right? Like Mr. Brock, I don't think we factored x to the 5th equations. We haven't done that. That's probably true. We haven't done a lot of time with x to the 5th. We've done a lot of quadratic factoring over our algebra lives here in the last algebra classes and all that. We've factored that. Occasionally, maybe an x to the third that we factored by finding the greatest common factor or pulling something out and simplifying that. But this looks a little different. Well, we know last week we learned that there's 5 solutions because it's an x to the 5th, right? The fundamental theorem of algebra. We learned through the factor theorem that we could divide numbers into it. We can use synthetic division or long division, and we could divide numbers in there. And if the remainder is zero, that would be one of the solutions. That'd be a factor. So we could do that. But what numbers would we want to do? I mean, x to the 5th, it could be a lot of different numbers, right? We can make a chart. We can say, okay, well, we'll start with 1, 2, 3, 4, 5, 6. We'll do 1 through 10. How about we start with that? And then we'll do -1 through -10 because, a lot of solutions a lot of times are negative. This could take all class, you think? They could take all class to find the factors of the. I mean, that's a lot of synthetic division. Well, if I tell you there's some shortcuts to that. This week, the theorem that we're learning, the rational root theorem, can narrow that down. So let's talk about the rational root theorem. All right, the rational root theorem. I'm going to write that over here. Rational root theorem. All right. At first start was a little funky, but after that, things improved. All right. So with the rational root theorem, it uses P's and Q's. P, Q. You've heard mind your P's and Q's? Well, maybe you haven't heard that. That's an old saying. It's actually an old British saying. It comes from like bars where they told people to mind their pints and quarts, because they got a little rowdy in the bar, start having, spilling beer everywhere. Mind your P's and Q's, mind your pints and quarts. But people say that now just to behave yourself. Mind your P's and Q's. So what are we talking about P's and Q's? Well, let me highlight 2 things here. I'm going to highlight this, and I'm going to highlight this. What I highlight here, nothing really. It's a 1. I'm highlighting the coefficient. The coefficient of the largest term and the constant at the end. So Q, we're going to define Q is all of the factors of the first coefficient, which in this case, Q equals 1, because that's the only factors of 1. P is going to be all the factors of 6. Now, this is plus or minus 1. Plus or minus 1. Because we can take -1 times -1 and get 1. 6, the factors of 6 are plus or minus 1 and plus or minus 2, plus or minus 3, plus or minus 6. Right, we could take 1 times 6, and that'd be 6. Or we could take -1 times -6, and that'd be 6. Or we can take 2 times 3, and that's 6. Or -2 times -3, 6. But that's pretty much all the factors. There's not any other numbers we can multiply together to get 6. So the rational root theorem says if we take P over Q, which P being all the factors of the constant and Q being all the factors of the coefficient of the largest term, if we put P over Q, so all the possible combinations, in this case, it's 1 over 1 plus or minus 1 over 1 plus or minus 2 over 1 plus or minus 3 over 1 and plus or minus 6 over 1. So that simplifies to just plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. All right, so that's P's over Q's. All right, I see what you got there, Mr. Brock, but what good does that do us? What good does that do us? We've got 8 numbers. We've got 1, 2, 3, 6, -1, -2, -3, -6. We've got 8 numbers. 1, -1, 2, -2. I'm going to write them with the positives on one side and negatives on the other side. Well, what the rational root theorem says, these are the only possible numbers that could be a rational root, that could be a solution for this. This is the only numbers that could possibly be a solution for that equation. Now, here's the key word: rational root. There could be some irrational roots where our answer is 2 plus the square root of 11 over 3. Right? That's an irrational root. We could have irrational, and we could have complex roots, imaginary solutions. There could be imaginary solutions as well. But as far as the rational roots, like when you graph this, this will be the whole numbers, the fractions that are the roots, that are the zeros, or where it crosses the x-axis. There's only 8 possible. So that means we can do synthetic division with these 8 numbers and find all the possible rational roots that way. We don't have to do 4 and 5 and -4, -5. We don't have to do 0, all those other numbers. We were going to do 1 to 10 and -1 to -10. We can rule all that out. We got it down to just 8 numbers. So that's a big help. But let's also talk about Descartes' rule of signs. Descartes' rule of signs is interesting because it's going to tell us some more about which of these numbers are the solutions. Kind of. So I'm going to write this again. I'm going to write our equation again because we're going to see what Descartes' rule of signs tells us. And yes, it's exactly what it says. We're looking at the signs of the terms. I don't care that this is a 4 or a 2. I care that it's a -4 and a +2. That's what counts in Descartes' rules of signs. So if we look at Descartes' rule of signs, how many times does the sign change? Well, this is a positive. This one's a positive, so there's no change there. This is a positive. This is a negative. Oh, there's a change right there. There's 1. The sign changed. It changed from positive to negative. What about the next one? Oh, still a negative. It didn't change. Still a negative. Still a negative. 1 sign change. 1 sign change. So, since we looked at the equation and the sign only changes 1 time, here's what Descartes figured out. Only 1 positive rational solution. Only one of these is going to be a solution on the positives. Only one of these. Because Descartes' rule of signs tells us there's only 1 positive rational solution. So if we're doing synthetic division and we get to maybe 1, if we divide 1 in there and it has a remainder of 0, 1's a factor, we can scratch out the rest of them. There's no need to even check them because there's only going to be 1 positive solution. And once we find it, we can stop checking the others. There's no need to continue. Great. That can eliminate more. We may not even need to check 8. But what about the negative ones? Oh, Descartes' rule of signs works for that too. If we take this original equation and we rewrite it by substituting a negative x into it. All right, so this is going to be negative x. Oh, that's not squared. That's supposed to be the fifth. Mr. Brock, you wrote the equation wrong. To the fifth plus 2 times negative x to the fourth minus 4 times negative x to the third minus 4 times negative x squared minus 5 times negative x minus 6. Now we have to simplify that, of course. So negative x to the fifth power. So that's negative x times negative x times negative x times negative x times negative x. So what's that going to end up? Well, when you have 2 of them, negative x times negative x, that's going to be a positive, right? Because negative times negative. And then these two, every time you have a pair of them, it makes it a positive. Positive times a positive. But we got one extra one. So it is going to end up negative x to the fifth. Because anytime you have an odd number of them, you're going to end up with a negative answer. If it's just an even number of them, they're going to end up a positive. So this next one, negative x to the fourth, is going to end up just x to the fourth, positive. So positive x to the fourth times 2. So this is 2x to the positive. So it's positive. Nothing changed there. This is a negative x to the third power. So that's going to be a negative x to the third times a negative 4. So a negative 4 times a negative x to the third makes that a positive. When we simplify. This one, negative x squared, negative x times negative x, that's a positive x squared times negative 4. So negative 4x squared. Negative 5 times negative x is a positive 5x. And then we have the minus 6 at the end. So this is f of negative x. Substitute negative x in. How many sign changes do we have? Starts as a negative. Changes to a positive. Oh, well, okay, there's one sign change. Still a positive. Still, oh, nope, it changed to a negative. So this is our second change. Still a negative. Did I do anything wrong here? I'm just trying to check my math. Okay. So right here, oh, that changed from negative to a positive. So that's our third sign. And a positive back to a negative. Okay. So there are 4 sign changes. So that means for, I'm going to put this word in there and I'm going to talk about why. Possible negative rational solutions. So it's very possible that all 4 of these could be rational roots for that equation. Because Descartes' rule of sign says there could be 4 of them. Mr. Brock, you keep saying could be. You said there was one positive one, but you keep saying there could be 4 negative ones. Yes, I'm saying that for a reason. Because we don't know at this point if there's any imaginary solutions. We don't know if any of these are imaginary solutions. Now, let me talk about imaginary solutions for just a moment. It is possible to have imaginary solutions and end up like 3 plus 2i, something like that. But if you have an imaginary solution, and we won't know at this point with what we've done, we won't know until we start figuring out which of these are there. If you have an imaginary solutions are kind of needy. I'm going to say it that way. They're kind of needy. They're not very confident. They won't go anywhere by themselves. Let's say if If, and I'm going to say this, 3 plus 2i is a solution. If we do the work and we find out that 3 plus 2i is a solution, we said, oh, we have an imaginary solution. Then 3 minus 2i is also a solution. Oh, that's good to have in your notes. Imaginary solutions always, I'm putting this in all capital letters, come in pairs. I'm going to highlight that and I'm going to underline it in red. Imaginary solutions always come in pairs. So if you have this one, you have its conjugate. Conjugate. I'm going to put that in our notes. The conjugate is the exact same numbers. You just changed the sign. 3 plus 2i and 3 minus 2i are conjugate. They're conjugates of each other. So if we find out that there's an imaginary solution, there's going to be two. So Descartes' rule of signs won't tell us if there's any imaginary solutions. It'll just tell us how many possible solutions there are. So that means if we look at this whole equation up here, there could be, let's see, what's possible. What's possible? Let's see. We're going to say positive, negative, or complex, which has an I in it. Here's what's possible for this equation. Under any circumstance, there's going to be one positive. And we know it can't be imaginary. It can't be imaginary because imaginary solutions always come in pairs. So that's why we know if there's one, there's definitely one. Because there's no way it could be imaginary, or there'd have to be two. So there could be one, and there could be 4 negative solutions, because that's what this told us here. That means there would be no imaginary solutions. All right, so that's one possibility. The other possibility is there's going to be one positive. Maybe 2 of these are imaginary solutions. So that means there's only 2 actual negative rational solutions, because it turned out there was an imaginary solution and it came with a buddy, because it's very insecure. He's not very confident. He has to bring a buddy along. So there could be 2. The other scenario that's possible then, again, there's going to be one positive. Maybe there's 4 imaginary solutions, because 2 imaginary solutions came and brought buddies. That means there would be no negative solutions. This is the only possibilities. There's definitely one positive solution. There's either 4, 2, or 0 negative solution based on how many of those solutions are actually imaginary numbers. Because imaginary numbers always come in pairs. So when you're figuring out what's possible, you have to deduct pairs. If this number is bigger than 1, it's possible it could be imaginary. All right, Mr. Brock, you've teased us here. Let's find some solutions. Yes, let's do that. We're going to start with number 1, and we're going to do some division. We'll do synthetic division. We'll see if I can show some more of the page here. We'll do some synthetic division using this 1. So if we divide 1 into, remember, all we have to do is take just the coefficients, 1, 2, -4, -4, -5, and -6. And we're going to divide 1 into it. Remember, we just bring that down. 1 times 1 is 1. Add those. 1 times 3 is 3. Add those. 1 times -1 is -1. Add those. 1 times -5 is -5. Add those. 1 times -10. So this has a remainder of 16. 1 is not a solution. All right, let's check 2. 1, 2, -4, -4, -5, -6. The 1 comes down. 2 times 2 is 4. I mean, 2 times 1 is 2. 2 plus 2 is 4. 2 times 4 is 8. Add those. That's a +4. 8. Add those. +4. 8. Add those. +3. 6. Oh, remainder of 0. So this is a solution. We do not have to check 3 or 6. We don't have to check 3 or 6 because we know there's only one positive solution, and we just found it. It's 2. So x minus 2 is a factor. And if we factor it out, that means since we started with an x to the 5th, 1x to the 4th, and these are positives all the way across now, plus 4x to the 3rd plus 4x squared plus 4. Well, how do I get that? 4th? Yeah, plus 4x plus 3, and a remainder of 0. So if we factor out the x minus 2, that leaves just this. All right. Well, let's see if -1's a factor. And we can actually start with this now because we've already factored this out. So we can change what divided by. Let's check the negatives. Let's look at -1. Let's see, -1, and we will divide that into this one. Just 1, 4, 4, 4, and 3. So that comes down. 1 times -1, -1. That's 3. 1 times -3 is 3. That's a 1. 1 times -1 is 1. So that's 3. 1 times -3. That's another factor. So -1 is a factor. Okay, because we have a remainder of 0. So that tells us this is a factor. And now we've got x minus 2. That's a -1. So x plus 1 is a factor. And that leaves us, since this was a 4th, this is a 3rd. X to the 3rd plus 3x squared plus x plus 3. Oh, we're narrowing it down here. We found 2 solutions so far. We found 2 factors. So let's continue on. We're going to try -2 because -2 is still a possibility. We have the coefficient of 1, 3, 1, and 3. That one comes down. -2 times 1, -2. Add that is 1. That is -2. Add that is -1. -2 times -1 is 2. And that's a remainder of 5. So -2 is not a solution. Let's try -3. Same equation. 1, 3, 1, 3. 1. -3 times 1 is -3. Add those, that's 0. -3 times 0 is 0. That comes down as a 1. -3 times -1 is -3. Up. -3 is a solution because it has a remainder of 0. -3 is a solution. So that means we now have x x minus 2 times x plus 1 times x plus 3. And what's left? X squared. There's no x plus 1. X squared plus 1. Do we need to check -6? This says no. Because if -6 was the solution, that means there would be 3 negatives. 3 negatives is not possible. There's either 4, there's 2, or there's none. We don't have to check -6 because there's no way it can be a solution. Because Descartes' rule of sign says there's either 4, there's 2, and there's 0. Since we found 2, we found 1. We knew there had to be at least one more, but maybe all 3. But when that one got crossed out, that means one of these had to be 1 because that means there's 2. So this is what we ended up with. So let's see what those 2 complex solutions are. And we can figure that out now. We can't always, if there was 4, we'd have trouble. We'd have to do some different work. But we just have to find what the solutions for this are. X squared plus 1, set it equal to 0. Subtract 1 from both sides. X squared equals -1. Take the square root of both sides. X equals plus or minus the square root of -1, which means plus or minus I. Plus or minus I. So the factors are, well, the solutions are, let's start smallest to largest. We'll go -3, -1, 2, I, and -I. There's our 5 solutions. If you want to put this in complex number form, because we talked about it like this, it's actually 0 plus 1i and 0 minus 1i. 0 plus 1i, 0 minus 1i. These are all the same. I and -I, 0 plus I, 0 plus 1i. They're complex solutions. They're imaginary. 3, -3, -1, 2, I, and -I. Like, wow, let's see if we're right. We're gonna go right here to Desmos, the graph calculator, and we're gonna put this equation in and see what it looks like. So let me type this in here. F of x equals x to the 5th was our first term, plus 2x to the 4th, minus 4x to the 3rd, minus 4x squared, minus 5x, minus 6. Whew, boy, what a mess. Well, let's clean this up a little bit. Take off the minor grid lines and make these go by 1s. Okay, so now they go by 1s. All right, let's see what the graph looks like. We zoom way out. Ooh, it's this really kind of odd-looking, sharp-cornered thing. But if we look at the solutions, the zeros, we've got one at -3, we've got one at -1, and we've got one at 2. We've got one at -3, we've got one at -1, we've got one at 2. And these are imaginary, so they don't show up on the graph. So we took this really long, put up there where it looks a little bit. Took this really long equation that we started class with, this x to the 5th, and we found all 5 solutions right there for that equation in about 30 minutes, which we thought could take us all class to find all the solutions of this, because you guys sit there and divide and divide, divide. But the rational root theorem narrowed it down to only 8 possible solutions. And then when we had Descartes' rule of signs, how many did we test? We tested this one. We tested this one. We did not test those 2. We tested this one, and this one. And so we only tested 5 numbers. with all the possible numbers we were thinking that we'd have to check to figure out the solutions to that, we only had to check 5 numbers, and 3 of them were solutions. And there's only going to be 5 solutions because it's the x to the 5th. So that is Descartes' rule of signs and the rational root theorem in action right there. I'll take pictures of these 2 pages and put them in our Google Classroom under notes for this week. But here's an important thing to remember. This will mess you up if you don't remember this. That's great for your notes. Imaginary solutions always come in pairs. So 3 plus 2i is a solution, then 3 minus 2i is a solution. Or in our case, I was the solution and negative I was the solution. It was just 0 plus I, 0 negative I. Use these things, the rational root theorem, use Descartes' rule of signs. We used the fundamental theorem of algebra. We used the factor theorem. That's a factor with a remainder. We didn't use the remainder theorem. We could have substituted 2 into the equation instead of divided it by 2. It would have got the same result if we just put 2 in for x. You can do it that way. So it gives you a choice either way. Now let's actually look and see what the lesson has to say about this. But we've seen it in action right here. We've looked at an entire problem, a big nasty problem like that, and worked through it with our 2 theorems. All right, so let's go to the rational root theorem lesson here. We won't spend a whole lot of time going through the examples in the lesson because we just did one from scratch. Now that one is actually in our lesson, and I think they have some videos and stuff. So if you need a refresher on how we got there, you'll have that opportunity. But let's see. Yeah, here's that same thing. X to the 5th plus, it's the same problem we just played with. Take a look at this function. Right, so the fundamental theorem of algebra said that there are 5 zeros. Since the degree is 5, there's 5 values of x that make it equal to 0 right there. 5. So, okay. It says checking to see if 1 is one of the solutions. That's one of the things we did. We went through the synthetic division with 1, and we found out that 1 was not a solution when you go through those. And they walk through it here too. So if you want to go back and review synthetic division here, they're doing it right here because they come up with that remainder of negative 16, which says this is not a solution. We did the same thing. Okay, so it would be very time consuming to test every real number to find the 5 solutions, right? We talked about that. There is a better way. There's a better way. So that's where we talk about, this goes through all the same things we went through, the P's over Q's. So if you need a refresher on what P and Q is, it took the coefficient of the largest term and took the constant term at the end and did all the factors to rule it down to those 8 numbers that we ruled it down to, the possible positives, the possible negatives, and they went ahead and did the synthetic division on all 8 of them because they hadn't talked about Descartes' rule of signs yet. I combined those. You see, they went ahead and did all 8. And look, boy, when you did number 6, it got huge. The remainder is 9,324. But we used Descartes' rule of signs and said, we don't even need to check that. Here's another solution, finding the rational zeros of this. I do want to do one more example just to look at the P's and Q's part again. So we'll do that in a moment here. Descartes' rule of signs. So here's where they go the same thing. Here's the possible number of complex zeros. This is the same chart that we made when they get to the bottom page. You can go through this if you want a refresher, but this is what I just did on paper. But there's 5 possible zeros. We know there's 1 positive one, and their negative could be 4, 2, or 0, which means complex is 0, 2, or 4. Same thing that we did. So this steps through everything that we just did on paper for Descartes' rule of signs. All right, so here's some videos in here, which is great. So I won't necessarily go through these since you can watch the video. This video is 4 minutes. and it takes this equation right up here and finds the possible number of positive, negative, or complex zeros. When it gets to the end, there you go. Spoiler alert. No, just two different options there. And let's see what she's doing there. That's another 4-minute video where she is starting to check some of those numbers. So this is a good one for us to write down. I'm going to write down the one she has right there, just to kind of step through the P's and Q's thing again, because we didn't spend much time on that. We won't go through finding all the solutions. There's a video where she starts talking about that. But I just want to go over the P's and Q's thing just to make sure everybody understands that. And we have a little more practice together where you practice it on your own. All right, so the P's and Q's thing. Let's look at that again. All right, if we have this one, here's 2x to the fourth. So we know there's 4 solutions, right? We know there's 4 solutions because we've got that highest exponent of 4. 4. But what are those possible solutions? So let's look at, we won't find the solutions, but we'll look at the P's and Q's, and we'll go through DeCartes' rule of signs again, just to determine how many there could be. So the Q is based on that. And the P is based on the constant. The Q is based on the coefficient of the largest term. So P's over Q's. What is the possible P's? 1, 3, 9, right? 1 times 9 or 3 times 3. And these are all plus or minus. That's the possible factors of 9. Factors of 2 is just 1 and 2, right? 1 times 2. So if we put every possible P over every possible Q. So let's take 1 first. 1 plus or minus 1 over 1 and 1 plus or minus 1 over 2. Okay, now let's do the second one, the 3. 3 over 1 plus or minus and plus or minus 3 over 2. That's all the possible Q's now. Let's go to the next one. Plus or minus 9 over 1 plus or minus 9 over 2. So the possible rational solutions to this equation, let's simplify this. Plus or minus 1 over 1 is just 1. Plus or minus 1/2. See, it'll even tell us if there's possible fractions. 1/2 could be a solution. Plus or minus 3, because 3 over 1 is just 3. Plus or minus 3/2. Plus or minus 9. And plus or minus 9/2. So there are 12 possible rational roots, rational solutions. And 3 of them are fractions. 3 of them are fractions. Let's see how many possible positive, negative, or complex there are. So if we look at this again, I'm just rewriting it so we have some space to work under it here. Okay, Descartes' rule of signs. This is the positive. This is a positive. Oh, it changed right there. There's one change. Negative. Oh, changes again. 2 sign changes. So that means when we make our chart down here, I see positive. I'll put those as positive solutions. Negative, complex, which would have an I in them. And total, we know there's a total of 4 solutions. So far we've got 2 different choices. Could be 2 positive, or there could be 0 if they're imaginary. Remember, well, we don't know yet. We have to change that. But let's see, complex. We may have to add more columns. Let me move that over in case I do. 2 or 0, but it could be 2 complex and 0 there. Let's check the negative. F of negative x. 2 times negative x to the 4th plus negative x to the 3rd minus 19 negative x squared minus 9 times negative x plus 9, which simplifies to, this is the even, so that's going to end up a positive. This is an odd, so that's going to change that sign to a negative. This is going to be a positive, so that's going to stay a negative. This is a negative times a negative, so that becomes a positive, and that's positive. So how many sign changes? Positive to negative, there's 1. Negative to positive, there's 2. So we have 2 again. So, yeah, we're going to have to add more columns on there, I think. So. May even need more than that. So there could be 2. Oh, wait. If they're complex, then there's not going to be any negative because there's 4 total. Right? There's 4 total. So it could be 2 positive and 2 complex because maybe there's no negative ones. Or maybe all, no, there can't be, let's change it. There can't be 4. There's either 0 or 2. So it could be either, let's put this option. There's 2 positive and 2 negative, which means there's no imaginary. 2 positive, 2 negative, no imaginary. 2 positive and the negative ones are actually imaginary, or the positive ones are imaginary. Or I guess there could be no positive, no negative, and 4 imaginary. So 2 or 0, and this is 2 or 0, because remember, they come in pairs. So there's 4 possible solutions. Could be 2 and 2, 2 and 0 with 2, 0 and 2 and 2, or 0, 0 and 4. So there's our possible. We're not going to find all those solutions, especially if it ends up this one, because that would be something. But when we start checking these 12 possibilities, once you find 2 positive ones, you can stop. Once you find 1 positive, you know there's going to be a second one. And the same thing with the negative numbers. If you find 1, you know there's going to be a second one. But once you find the second one, you can stop. You don't need to check them all. There's not going to be more than 2 positive. There's not going to be more than 2 negative because of the Descartes rule of signs. So let's see. All right. And she put her little charts up here. Figuring all that out as well. Okay, here's another example. Oh, this is negative 7x to the 5th. And it walks through all the same stuff. How many times does the sign change? This is where, for your practice, look at that, figure out how many times the sign change, enter that there, submit. So how many zeros are there? Based on your answer here. Then the negative. When you substitute the negative x in there, what's it look like? Here's what it looks like. So try it on paper first, and then you can check and see, did you do it right? Did you simplify it correct, the same as they did? Then how many times does the sign change in f of negative x? So how many negative zeros are there? And then, so that leaves imaginary. How many total zeros right there? And what's all the possible combinations? There's 4 possible combinations of that one. Here's another example in Descartes' rule of signs, if you need to see it again. Well, it's not going to load. It's being very, very naughty today. Try it one more time. There it goes. Okay. So there's another example using a 4th degree function, 5x to the 4th. So you can print that out. That's more for your practice and your notes. Let's see. Did it cover, what else did it cover in this lesson? Let me look at that. Sketches. Yes, we have not talked about sketching graphs. Okay. So let's do that. In fact, let's do that with this graph we have right, this equation we're using right here. Let's do that with this equation we have right here. We're going to talk about sketching graphs in this equation, using this equation. Sketching graphs means, okay, it's not going to be exact. This is not going to be the exact graph, but it should look like the graph. There should be a few points that are correct. Actually, we can't do it that. We don't have the zeros on that. We can do it. We can do it with this original one. Let's do it. Let's do it with this other one. What's that? Oh, it's on the other side. We can graph this one because we've already factored it and everything. We know the zeros. Okay, so if we were going to graph this, and we're just going to sketch a graph of it, we actually already know what it looks like because we did graph it. We know of one thing. Let's see, x to the fifth. X to the fifth. It's an x to the fifth equation. So here's what we know. I'm going to draw this box down here. If it is even, odd's going to be our other option, right? If it's an even equation or an odd equation. Now, how do we know if it's an even equation or odd equation? It's all based on the largest exponent, which in this case is the fifth, right? The largest exponent. Is that an even number or an odd number? That's all you need to know. Is it even or odd? Well, that's an odd number. So on an odd numbered graph, the left side is going to point down and the right side is going to point up if the coefficient is positive. If the coefficient is negative, the left side is going to point up and the right side is going to point down. So with ours, this is a positive coefficient. So we know that this end of the graph is going to be pointing up and this end of the graph is going to point down. So we've already started our graph sketching. Let's see. We know on an even one, let's go ahead and do that. Both ends are going to point the same direction. If it's positive, it's going to be pointing up. If it's negative, it's going to be pointing down. So if we're sketching an even one, like x to the fourth or x squared, like a parabola would be an even number, x squared, and they both point up or both point down. Odd ones this way. What else can we tell by this? Well, on this one, we have the solutions. We have the solutions of -3, -1, and 2. So let's say -1, -2, -3, 1, 2. We know that there's a solution there, a solution there, and a solution there. And the other ones are imaginary, so they wouldn't show up on the graph. What else do we know about this? We know, just looking at this equation, what the y-intercept is going to be for the graph. Because the y-intercept is when x is 0. So if x is 0, that's 0. That would be 0. -4 times 0 to the third, that'd be 0. Everything with x is going to be zeroed out. That just leaves -6. So since that's -6, 1, 2, 3, 4, 5, 6, that tells us that that is the y-intercept. So just by looking at the equation, we know what the y-intercept is. -6 on the end, that's what it's going to be. So now we know enough to sketch it. We know it goes up here, so it's going to come down through that point. It's going to come down through here. And somewhere up here, it's going to turn around and come back down. This would just be a sketch. If we said graph the equation, you got to be more accurate. If we say sketch the equation, this is good enough. Now, this one we actually did graph. Ours kind of similar. Actually, on the real graph, this went down further and was coming back up when it went through that. But that's okay. as long as we have the intercept correct. Actually went down farther and comes up through that 6. We see that right there. See, because there's the 6, the -6 right there. But we would go through these 3 points. So a sketch of a graph. So sketching graphs, the important thing to know is which way do the arrows go? Is it plus or minus? So that tells you. And then you can just take the solutions and graph it. All right. So that's what this is talking about. You can go through the lesson and look and see what example it gives you, because she takes this with the solutions and she graphs this equation, 2x to the 4th. So let's see, how long is that video? Minute and a half. So if you want to watch that minute and a half video, finding the y-intercept, it's just that number on the end because everything else zeroes out. Finding the zeros, Descartes' rule of signs, rational roots, uncovering the zeros, just dividing those possibles in there. There's the lesson summary. They have practice problems on page 5 for you. So there's your practice problems. Activity 1, activity 2, activity 3, and there's like 2 problems here. Find all the past possible rational roots. That's at P over Q. So which of those would it be? Activity 2, use the rule of signs. Check your answer. And then there's another one here, a different problem and a different problem. So there's 3 of those for you to practice. And then activity 3 is sketch the graph. Sketch that, and then you can check it to see if you're right. All right, let's look at the next lesson real quick. Oh, I think it's going to make me do this. Let me just answer one thing. I'm going to say it's that one. All right. I have to turn something in, or it won't let me look at the next lesson. I got that one right, at least. Okay, solving polynomial equations lesson. This just puts together everything that we've done in the last ones for the most part. I think we add one piece. We're going to add one piece here that we didn't look at in there. So you've actually been doing algebra forever at a very young age. You just didn't realize it. Like in elementary school, you probably had something like this. Blank plus 6 equals 10. Well, that was algebra. Was just later on, we just gave the blank a name and called it X. So you've always dealt with algebra ever since you were doing blank plus 6 equals 10. So we just got more complicated. We finally changed that blank to a name, and then we started making it a little more complicated by making 2 times that blank plus 6 equals 10. And then we added more variables. It got more and more complex. So you're doing quadratics. So you just started out real simple and kept going on. So here is the 5. Here are, I shouldn't say here is. English teachers get mad at me when I do that. But I do it and have fun. I don't know. Here are the 5 things that we've looked at in the last few lessons that are really good. The fundamental theorem of algebra, the rational root theorem, Descartes' rule of signs, the remainder theorem, and the factor theorem. And you can click on here for reviews of any of those. You're like, what was that one again? Right. So you can click on, there's the reviews. And then here's another sample problem. X to the 3rd plus 3x squared minus 22x minus 24. And here's how to use those theorems to find the solutions. All right. So again, I'm not going to go through another example. You can go through those steps. For example, here's lots of videos in these lessons, which is great. Using the rational root theorem. That's an 8-minute video where they go all the way through this and then go all the way to the graph. Doing all these solutions, finding the zeros, using those theorems to rule out numbers, using the P's and Q's. Figuring out how many positive, negative there could be. Fundamental Descartes' rule of signs. So this puts a lot of it together right here, rational root theorem. So this was a great video. If you're still struggling with this, if you try those example problems and are still struggling, here's a great video that puts a lot of it together. All right. And then sketching the graph. This talks about that again. Determine the zeros of this equation. Again, here's the steps. What's the P? The P value. Well, on that one, the P is over here, so that's the 14, right? Submit. Yep, that's the 14. And then it says, okay, what's next? What are the factors of 14? plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. Yep. That's it. And then I'll probably ask the Q. The Q on this one is just a 1. And then it wants to know what are the factors of Q? 1 and negative 1. Because we can multiply 1 times 1 or negative 1 times negative 1. Oh, it wants me to put it in the other order, I think. Oh, least to greatest. Yeah, negative 1 to 1. I didn't do least to greatest. Yeah, see, that's it. And then it wants you to do the plus or minus, putting each over the top. So, all right. When complex zeros are discovered, sketching the graph can be difficult, right? So the fundamental algebra indicates there's 4 zeros, but it turns out there's only 2 real zeros. So that's when we get a little tricky on that. So we can't just graph it and find the zeros, because a lot of times there's imaginary zeros. And remember the conjugate, right? Like if you have 3 minus square root of 5, a conjugate is 3 plus the square root of 5. So like on the imaginary, 7 plus 10i would also have 7 minus 10i as the other imaginary solution. Here's more on solving polynomial equations. And we solved them using these 5 theorems we just had. And again, another example that you can go through to determine the zeros. You need help with that. All right, let me see. Where's the one other thing I want to add? There it is, right here. All right, let me turn over and get a blank side of this paper. Negative 4, 3, and 7. All right, so if I tell you, all right, zeros of negative 4, 3, and 7. Okay, let me sharpen this pencil real quick. We're wearing it out today. All right, if I say, okay, I've got a function that has these zeros. What's the function? You're like, Mr. Brock, you've only given me the zeros. Yes. What's the function? Mr. Brock, I don't know the function that has those 3 zeros. Well, can you find the function? I'm not sure. You can. Because let's just take what we know about these zeros. If this is a 0, here's one of the zeros. X equals negative 4. So what's that factor? If x equals negative 4, what's that factor? Well, let's put that back over equal to 0. X plus 4 equals 0. X plus 4 is one of the factors. Going backwards. Because when we had x plus 4 as a factor, we said equal to 0, we found that x equal negative 4 was the solution. So if we go backwards and put it back into the factor form, that's one of the factors. Well, also, x equals 3. So what factor is that? Well, that's x minus 3. There's a factor. Well, by the same token, then there's a factor. So what's the equation? Well, it's x plus 4 times x minus 3 times x minus 7. Yes, but let's simplify that to standard form. That is a function right there. But let's just multiply these back together. X plus 4, we'll do the first ones together first. So, right, we just distribute. We take the x and multiply it by both terms. And then we take the 4 and we multiply it by both terms. So we'll do these two first. X times x is x squared. X times negative 3. 4 times x. And 4 times negative 3. And we still have x minus 7 down here. Now we can combine like terms. So this is x squared plus 1x, and negative 3x plus 4x, Well, it's really bright. There we go. Minus 12 x minus 7. Great. Let's just do it one more time. This time, you can put them in the other order if you want to do it that way, but we'll leave them in this order. We got to do this times both of them. Then we got to do this times both of them. And then we got to do this times both of them. So x squared times x is x to the third. X squared times 7 is negative 7x squared, because that's a negative 7. X times x is x squared. X times negative 7, negative 7x. Negative 12 times x. And negative 12 times negative 7. Now, what like terms do we have? These are both like terms. Those are both like terms. So let's combine those. So the function is x to the third, negative 7x squared plus a positive x squared. Negative 7x minus 12x is negative 19x plus 84. This is the function that has these zeros. Let's verify. We can check our work. We can go right here. If we said the function was x to the third minus 6x squared minus 19x plus 84, does it have the solutions of negative 4, 3, and 7? It does. We just checked our work. Negative 4, 3, and 7 is the solutions. And that's what we needed. We needed negative 4, 3, and 7. And this is the equation we came up with. So yes, you can do this. You can just put the factors and then multiply them back together, and you can come up with the equation in standard form for those solutions. So that was the other part it has here. Find the polynomial function whose zeros are negative 4, 3, and 7. And they work backwards just like we did. Come up with those three factors and then multiplied them back together and got to the same place. And then you can check your answer. How'd they check the answer? They check the answer by finding the factors that, look, there's the P over Q. There's lots of choices there. They did the sign change thing and worked through that way, finding that when you divide by 3, all the way down, confirmed them all. Once they found one factor, that left them a quadratic, and then they just factored the quadratic. Here's another one. Has a negative 2 with a multiplicity of 3 and 5. I'm not going to work this all, but we'll set it up real quick. Negative 2 with multiplicity, that's a fun word to write, of 3 and 5. And they said, okay, what's this equation? Well, you can set that up. If negative 2 has a multiplicity of 3, it means actually the solutions are negative 2, negative 2, negative 2, and 5. Multiplicity of 3 means there's 3 of them. So that means you would have x plus 2 times x plus 2 times x plus 2 times x minus 5. That's what you multiply together. If it said you had the solutions of this is where they get tricky, because they'll do this to you. 1, 4, and I. Zeros or solutions. Solutions with zeros are 1, 4, and I. Could you write that equation? Because they will try to fool you there. They will try to fool you here, because remember, all right, so we could say, okay, x minus 1 and x minus 4 and x minus I. You say, I just multiply those together, right? Oh, let me find this sheet of paper. Let me see. What did I put in red and circle the big box? Imaginary solutions always come in pairs. They're trying to trick me right here. If I is a solution, negative I is also a solution. I've got to add that, x plus I. Now I can multiply them together. They didn't tell me this one. They just gave me 3. So this is actually an x to the 4th, because there's 4 solutions. They had me thinking it was an x to the 3rd. Don't let them fool you. If they give you one imaginary solution, the other one is also there. Don't let them fool you on that. All right. So they work through that. Let's see. Did they? Yeah, here's one with an I. They said 1 with the multiplicity of 2 and 5i. Well, if 5i is a solution, you got to add the negative 5i. So they go through the example there. So there's several examples and the lesson summary. So that's the end of that. So, all right. I know I threw a lot at you today, but I got through it 10 minutes faster than I did yesterday. So just a lot to it. So you have 5 different big pieces that you learn. Theorems, the fundamental theorem of algebra, the rational root theorem, the factor theorem. We looked at Descartes' rule of signs, remainder theorem, all that great stuff in the last 2 weeks. Really good math things. They're really helpful. Pretty cool things that mathematicians have figured out over the years. Descartes was back in like the 1700s, so he's known that for a while. So, all right, guys. If you got any questions, I'm happy to answer them. Otherwise, we're done for today. That's plenty. This is an A day Friday, so we'll have class Thursday if you need help. And if you have less than a 70, I'll see you. But I don't think anyone here has less than 70 currently. So good work. Keep it up. So, all right. We'll see you guys.